So it's my great pleasure to present our today's speaker, and the title is kind of provocative. Do biological species exist as mathematical solutions? But I expect a very nice discussion about this title. And it's my great pleasure to present Professor Vol'pert, who kindly agreed to present his studies at our seminar. So thank you very much, and please go ahead.
Thank you very much for this presentation and also for the invitation to your seminar. What I'm going to discuss today is our recent work together with colleagues from Chile, University of Talca. It's Boris Pena and Sergei Kravchenko. And indeed, I'm going to discuss mathematical modeling of some biological questions, which seem quite interesting to me. We worked during many years already on related questions. So what I'm going to discuss today, I will begin with a short biological introduction about biological species and their characterization. Then, since we will try to discuss some mathematical modeling related to this question, so I will recall some classical models in population dynamics, and we will see that these classical models may not be sufficient to describe the questions we are going to discuss. So we'll derive another type of model, another type of equation. Then I will very briefly discuss mathematical results, because in fact mathematical results is not the main goal of my today's presentation. There are really very interesting mathematical questions. I will formulate some results, but I will not prove them. And after that, we'll discuss some biological interpretation, some mathematical interpretation. So it will be kind of discussions related to this model and to the biological questions. So first of all, what are biological species? There are different definitions, and maybe, I'm not sure, but probably the first one was given by Darwin, who defined species as a group of organisms or individuals determined by their morphology. What is morphology? It's size of some animals, their shape, their anatomical structure. Well, I think that intuitively it's clear what we talk about. There is no precise kind of mathematical definition of morphology. Later, another definition was given by Meyer. He defined biological species as a group of individuals that can interbreed between them, and this group is reproductively isolated from other groups. And more recently, biological species are determined by genetic analysis. Well, here in this image at the right, there's a nice picture with some butterflies, and in fact, oops, no, sorry, I did something wrong. I was looking for a pointer, but but instead of pointer, I get something different. Sorry, I'm still looking for a pointer. Yes. Yes, so very nice picture with different butterflies. So it appears that there are, for example, 20,000 species of butterflies. Okay, so coming back to Darwin's definition of biological species, first of all, I would like to mention that this book, you see the title page, it is considered as the most influential scientific book of all times. And it's a big book, about 700 pages, and it's passionate reading. And in the whole book, and there is only one picture, one image shown here, this diagram, and he used this diagram to explain his whole theory of biological evolution. And I will briefly stop on this because it is interesting, it is instructive, and I will use it further in my presentation. So each line in this diagram corresponds to one biological species. The horizontal axis here, well, he explains, of course, he does not give a precise, say, mathematical definition or whatever definition, but he describes that and he explains that the distance between these lines correspond to morphological differences between different species. So we can interpret this horizontal line as some morphological parameter, or in more modern language, some phenotypical parameter which characterize different species. And the distance between them is the difference in morphology. The vertical line here corresponds to time measured in generations. And this picture, this diagram shows how this species, meaning lines, how they evolve, and there are many things that can happen with them, and it's very interesting to analyze this diagram because it explains how Darwin thought about the whole living world, its evolution, and it's not only natural selection or emergence of species, because Darwin explains the emergence of species due to natural selection. So if we look attentively at this diagram, you see, for example, here from this point, there are several new lines appearing here, and this is how he explains the emergence of new species from all species. And we can also observe that not all these lines continue, only the most left and the most right, and he explained all that. There are also some other lines, meaning some species which continue like that, but then they stop, and this we should understand that this happens because of competition between different species. Or there are also some other lines, like here in the middle, which continue without changing, without bifurcations. So, so how we should understand this? That these lines correspond to different species. This is not so obvious question, and trying to understand that, I give the following interpretation. So, if we consider one biological species, and we understand that all individuals or all animals in this population, in this group of animals, they are not identical to each other. They have close morphology or close phenotype, but they are not identical to each other. For example, if we take the size of these animals as this morphological parameter, then we'll have some kind of distribution like that, some kind of spike in around some average value. So they are close to each other, they resemble each other, but they're different. So there's kind of such distribution like that, with some average value here corresponding to the maximum of this distribution. So we can probably interpret these lines on Darwin diagrams as positions of maximums of these distributions and how these positions change in time. So this is a more, well, I try to give a little bit more rigorous explanation, interpretation of this diagram. So what is important for us today is that in this interpretation, and according to Darwin's definition, biological species is a group of individuals with such kind of distribution like that, which is quite localized, but it's not just a single point, not a delta function, but this is a distribution. I put here these two figures from the left to the right. So I discussed a little bit this distribution from the right, which corresponds to such species which do not bifurcate, which do not give emergence to other species. Also, some of the species give this new species, emergence of new species. We discussed this question, the emergence of species and mathematical modeling how we described all that during already 15 years or even more. So I will not discuss this question about the emergence of species today, but I will discuss more the question about the existence of such distributions in mathematical sense. So how we can describe this biological species understood in the sense as some populations with close morphology or close something, we'll discuss it later, how we can understand this in the mathematical sense. And as an example, I will give several examples. For example, what is of course very well known, if we take a group of people and we measure their height, so then we'll have such kind of distributions which look very much like a normal distribution, a little bit different between women and men. And of course, this is similar to other biological species. There are many examples, in particular here, body size for different groups of animals. What we should also take into account is that these distributions, these morphological characterizations, they are quite stable. For example, here we see how the average male height changed during centuries. And if we put aside this last 100 or 200 years at the right, then we see that, but this it changes not significantly. We can say that it is more or less constant. So summarizing this, we can say that species, we can consider them as group of individuals with close morphology, and we can characterize them by some distribution with respect to this morphological or phenotypical parameter, and that these distributions are relatively stable in time. From this point of view, we can formulate the question whether such distributions can be obtained as stable stationary solutions of some mathematical models. And of course, we want to have these mathematical models biologically justified. From this point of view, I come back to the title of my today's talk. So I formulate that, do biological species exist as mathematical solutions? Exactly with the meaning I tried to explain before, as some stable stationary solutions of some mathematical models, of some mathematical equations. And since we begin to discuss mathematical models, so I will briefly recall some classical models in population dynamics. We will discuss whether we can use them in this case or we need something different. So in fact, models in population dynamics begin with Leonardo Fibonacci in 12th, 13th century, where he introduced Fibonacci sequences. And then it was a huge gap, 500 years, when Leonardo earlier introduced exponential sequences. By the way, it's a very interesting, well, we can say it, historical anecdote why earlier I began to study this question. And in fact, the reason for that was because, of course, he knew Bible, and in the Bible, well, one of the important stories was about this deluge, which well, eliminated the whole population, and only 3 families, 3 sons of Noah with their wife survived, and it was about like 2000 years before Christ. So earlier asked the question whether these 3 families were enough to initiate the whole Earth population, which he observed in the 18th century, with some estimates of the total population. And like that, he introduced exponential sequences, and he showed that indeed it was possible to obtain all this population beginning from 3 couples. I think it's a very interesting example of applications of mathematics. Then, of course, very important, very influential works by Thomas Malthus. It was not him who introduced exponential growth of the population. In fact, there are no any equations in his work. He explained everything with words, not with equations, but in fact he used this idea about, well, this rapid growth of population. So I don't remember, probably he did not call it exponential. There are many other very important and interesting ideas in his work, but we will not discuss, of course, today. And the next important step was done by Verhulst, who introduced this logistic equation. So not only this exponential part, but also this limiting part. So now we have something this grows with limitation, with iteration. Of course, very important, very influential works by Lotka and Vol'pert, but I will not stop on them because I will not use this today. And the next, also very interesting and important step was done in the works by Fisher and Kolmogorov, Petrovsky, and Poskunov in the 30s, where they added this diffusion term in the logistic equations. They studied this equation, and it was the first time when they introduced reaction diffusion waves, wave propagation in population dynamics, and it was the beginning of a huge development of these studies, which continue also now. So we'll see now how these mathematical models can be, or maybe not necessarily, can be used in this modeling and discussion of the question I suggested of the population growth and species and these distributions. So let us start with this model. We'll try to derive an equation and we'll see what it gives. So what we have here, we have three different individuals of three different, we can say, morphology, for example, body size, and we denote by U with subscript I the number of individuals with this morphology, with this body size, or it can be another morphological parameter. And then we say that first of all, these individuals can reproduce. So here there is a reproduction term. I will discuss it a little bit later. And then they can mutate, meaning that offspring can be a little bit different from parents. For example, when we start from parents like that, the offspring can be a little bit larger or a little bit smaller. Then if you do like that, and if we write the equation for the concentration of this ui, so this first term shows the exchange between this ui with this u, the next one, ui plus 1. This term describes this exchange with this ui minus 1. The next term is a reproduction term. So what is written here? In fact, this is the usual logistic term, but I put here also k, power k. This power k, if it is 1, it is exactly the logistic equation we discussed before. If k equal 2, it corresponds to sexual reproduction. So k equal 1 to asexual reproduction, k equal 2 to sexual reproduction, male, female. So this is a square. Then this is limitation, logistic limitation. And the last term is mortality term. So this equation, we derive it in this discrete form. Then passing to from the discrete to the continuous limit, we obtain such a reaction diffusion equation. Again, if k equal 1, it's exactly the same equation as written by, well, what is called KPP equation. Now, of course, in population dynamics, it's more general. Also, other form of nonlinearity are considered. In particular, we consider here k equal 1 or k equal 2. These are two different cases. So we have this reaction diffusion equation. So let us see whether this equation can give a solution like that, because we are looking for such kind of distributions. We say that for us, biological species is a distribution like that, which should exist and which should be stable. So let us see whether such equation can have such solutions. In fact, again, there are two different cases. If k equal 1, then we have logistic equation, and this logistic equation does not have solutions like that. It can be easily verified. I will not stop on that. If k equal 2, the situation is different, and in fact, such solutions exist. We call them pulse solutions. Pulse solutions exist, but they are not stable. This can also be easily proved by the analysis of the spectrum of the corresponding linearized operator. Again, as before, I don't stop on that. So the conclusion is that the equation like that cannot describe stable stationary solutions of this form. And then there are a number of developments of the theory for different cases. In particular, what is relevant for us today, we can consider space-dependent coefficients, or there is a whole theory, very interesting and quite developed now, devoted to non-local equations, non-local reaction diffusion equations. These are integral differential equations, in particular, where instead of this minus u, it here this term describes consumption of resources. If we consider non-local consumption of resources, it will be some integral here. What is interesting is that such more general equations can have solutions, these pulse solutions, but again, as before, it's not exactly what we are looking for, because it can be verified that for our problems, these solutions are not appropriate. So the conclusion is that if we consider this model, which of course with this very simple and very approximate derivation, which I presented, corresponds to this population distribution with respect to its phenotype. So this model does not have solutions of this form, and in fact, such models cannot describe biological species. With this conclusion, we now will try now to derive another model, and this model in this case will describe population distribution in respect to its genotype, not phenotype, but genotype. So this is, of course, a very important difference. Phenotype or morphological characterization, it's kind of body size or some phenotypical parameter, some other phenotypical parameter. And genotype is, of course, a different characterization. And so let us begin this derivation, and let's see how we can characterize population distribution with its genotype. So first of all, what we are talking about? We will characterize population or each individual in the population with its genotype. For us, of course, we don't go very profoundly in the biological theory. We'll take a very simple characterization. We'll consider that each individual is characterized by a number of genes. For example, here there are n genes, and each one of these genes can be in its original state called A, or in its mutated state called B. So like that, we have n letters A and B. So we have the sequence of letters, and in fact, we characterize this sequence of letters, like we use this notation A with the subscript n minus k and B with subscript k, means that there are k letters B and n minus k letters A. So in fact, since we say that B is mutated state, so we have here k mutations. So we have sequences of n letters written like that, and this index subscript k shows the number of mutations. So it's quite simple. And by UK, we denote the number of individuals in the population with k mutations. So the next step about these mutations, how it happens, let's see. For example, I take here as example this this sequence of 3 letters, 3 genes. And if there is only one mutation, so there are 3 possible cases shown here. This mutated gene B can be at the first place, at the second place, or at the third place. The first sequence we call A3B0, no mutations, and the second case A2B1, 1 mutation. What is important here to note that you see there's only one sequence here with 0 mutations, but 3 different sequences with 1 mutation, and all of them belong to this U1. So we consider all these 3 different cases with 1 mutation as they belong to the same subpopulation U1. This is important to take into account. So now we introduce the sequences, we introduce mutations, and now we can calculate the probability of these mutations. For example, if we have this UK and UK plus 1, let us calculate the probability of this transition. So we have the first sequence with A n minus k and BK. So there is 1 mutation of A to B. If there is only 1 mutation here from A to B, so we have less A and more B by 1. What is important here to understand is that this single mutation from A to B can happen for any of this A, for any. So in fact, this is why we multiply this, UK is the density, we multiply by n minus k because there are this n minus k possible places where this mutation can occur, mu probability of mutation. So in terms of rates, like reaction rate or whatever, transition rate, we have this rate written here. Exactly in the same way, we can now calculate all such transitions, probability or rates of all these transitions from UK to UK minus 1, UK plus 1 to UK, and UK minus 1 to UK. In fact, what is written here for cases which involve this population UK, transition to less mutations or to more mutations. So now it's very simple. We just write this equation for this population, subpopulation UK, this ordinary differential equation, take into account that this UK can be, as we discussed just before, can be either obtained from k plus 1 and k minus 1, or to the contrary, can give k minus 1, k plus 1. So we take all these terms in the right-hand side, and we obtain an equation like that. And of course, we write the same equations for all different cases. Then, just very simple identical transformation. What we do here, first of all, instead of k, I introduce xk. Just it's my purpose is to obtain a continuous equation. So already instead of this discrete variable k, I introduce discrete variable xk. But this is not what is important. What is more important is that I change the order of terms here. It's absolutely simple, identical transformation, just the order of terms in this equation. And what I obtain here, if I reorganize a little bit these terms, I will obtain an equation like that. You see, k plus 1 minus 2uk and plus uk minus 1. And of course, you can recognize here right away the discretization of this diffusion term. Then there are two convective terms written here, and this x, which appears already here. This is why after simple transformations and the change of variable, we'll obtain this convective term with this x, which is here inside the derivative. And finally, we add this logistic reproduction term. So like that, we derived our main equation written here. And we'll study now some properties of this equation. And we'll begin with the existence of stationary solutions. In the stationary case, I write the same equation that is shown here. Again, okay, I put the coefficients equal 1. It is not important for simplicity. This diffusion term, convective term, of course, with this x. This x is very important here. And logistic reproduction term. This equation is considered on the whole axis, and this r is some positive parameter. And let us begin with a simple example. And this example is where this coefficient r equals 0. Then we have this equation, u second derivative of u plus xu prime equals 0. And then there is an explicit analytical solution of this equation given by this normal distribution, in fact. So you see, it's kind of already indication that indeed we can expect solution like that, because in the simple case without reproduction term, we have a distribution like that. Then we do some mathematical study, and I will not discuss the details, the proofs and the details of the study. I will give this main existing results, which is formulated in the form of the theorem. The theorem gives a complete characterization of of solutions of this problem. Of course, it is difficult to read this slide, so instead of reading this formulation, I will illustrate this result with this figure. So let us try to understand what is shown here. And this is, in fact, the main result, the main mathematical result of this work, which I am presenting now. So, in fact, there are three types of solutions shown here. All the solutions which I consider now in this figure are symmetric with respect to x equals 0. It is not in here, but x equals 0 is here. So at the moment we consider these symmetric solutions, and there are three types of such solutions. This blue line shown here, it's a positive solution with such behavior at infinity. So it decays with the rate e to the power x squared with some polynomial factor. It's not just e to the power minus x squared as in the example, but here also this factor x to the power r. So if r is 0, it's exactly what we saw before. Now there is this factor and also some constant. So in fact, there is a unique solution which is like that. And besides this unique solution with over exponential decay, there is a family of positive solutions which are like that. So in fact, if we take as a parameter the maximal value of solution, the value at 0. So for all values of this parameter, there is a solution shown like that. It's a positive symmetric solution which decays at infinity with this polynomial rate. So again, there is a single solution with over exponential decay, and there is a family of solutions with this polynomial decay. And finally, there is another type of solution. If we take the value of the maximum, which is less than this blue solution, then such solutions also exist, but they are not positive. There are some negative values. Well, what I present now, it's not a complete characterization because there are some other solutions which are in this area or below in this area. I cannot stop on that now. The solutions are shown here are more interesting for us today. So this theorem characterizes all symmetric solutions. So if we consider not only symmetric solutions, but also asymmetric solutions, I have shown in this like a little bit symbolic schematic way, then to make it simple, I will not give the precise formulation. To make it simple, in fact, it's all possible combinations between behavior at the left half axis and in the right half axis. So we have three behaviors here, three behaviors here, so there are all possible combinations between them. I will not stop on that more. So we prove the existence of solutions, and first of all, we are interested by these symmetric solutions. Now, let us continue with stability of solutions. Again, there are some theorems, some results. I will explain it in a very simple way. It's shown in this, again, using this figure. So this is our equation, and we study stability of these solutions as stationary solutions of this equation. And in fact, the result, it's very easy to explain this result. In fact, let us take some positive initial condition. Well, mathematically speaking, it's a Cauchy problems, and there's some initial condition on the whole axis, all this, what we know. And then if the initial condition behaves at infinity as some stationary solution, if it has the same asymptotics, then the solution will converge to the stationary solution. Of course, we talk now only about positive solutions. So there are two types of positive solutions here with this over exponential decay and polynomial decay. In both cases, if the initial condition behaves at infinity as the corresponding stationary solution, then the solution of this equation will converge to this stationary solution. And of course, we should take into account that these polynomial solutions, it's the whole family of them which fill all these values. Well, we are also interested in other types of initial conditions which are not necessarily close to stationary solutions at infinity, but in biological applications, we often use initial conditions with a finite support. So if we take initial conditions with a finite support, then all such solutions will converge to the minimal positive solution. Minimal positive solution, it is a solution with this over exponential decay, with this, well, not exactly, but we can call it like normal distribution. So we have the unique solution like that. This unique solution is the minimal positive solution. And for all initial conditions with a finite support, the solution of the Cauchy problem will converge to this minimal positive solution with this over exponential decay. So this is all about mathematical results. Later I will say a couple of words, really only a couple of words about the proofs, on the maybe not the proofs, but the methods of proof. But the main mathematical results are here. It's the existence and stability of solutions of this equation. And now, in the last part of my presentation, I will give some conclusions, some remarks and comments, both about mathematics and applications. So, well, I started my today's presentation, and in fact, the purpose of this presentation was to answer this question: do biological species exist as mathematical solutions? Of course, in the sense as we defined before. So how to answer this question, whether these mathematical results can give, well, maybe not a complete answer, of course, because the question is very large, but maybe some elements of the answer. So we derived this equation which describes the population distribution with respect to the genotype. Of course, there were some simplifying assumptions. It's always like that, but well, in some sense, we can say that this equation is biologically realistic. So it is based on some biologically realistic assumptions. This equation has this normal distribution-like solutions, stationary solutions. And we show that all solutions of our problem with finite with initial conditions having finite support converge to this normal-like distribution. So from this point of view, we can say that indeed in some sense, our program was to derive a model and with certain solutions. From this point of view, we can say that indeed we obtain what we are looking for, and we can interpret such solutions as biological species. But if we talk about biological solutions and species, in what sense here we understand biological species? It is not in Darwin's sense, because we don't, I will return to this morphology, phenotype, but at the moment there is no morphology, no phenotype. So it's not according to Darwin, not according to Meyer. We don't discuss the reproduction here and separation of this reproductive groups from other groups. So we can understand that as biological species in the sense of derivation of the model. In fact, we consider here groups of individuals with related genotypes. In what sense related genotypes? In fact, what we did with this sequences of letters, our main assumption was that all the sequences of letters can be obtained from each other as random reversible mutations. So if we understand, of course, again, we should, of course, separate here strict mathematical results and interpretations. What I discuss now, these are interpretations, and interpretations, of course, not very precise. But still, if we interpret biological species as these genotypes characterized by these genotypes considered as sequence of letters, and if we allow them these random reversible mutations, then we understand biological species in this sense, and then we obtain this model and the corresponding solutions. So the next question then is, okay, suppose that we do all that, but then how this is related to Darwin's definition to morphology and phenotype. So this is the next question I am going to shortly discuss. In fact, well, to make a link between the genotype and the phenotype, we need to make one more assumption. In fact, that phenotype is proportional to the number of mutations. What I mean here. So let us take this well, the smallest individual, the smallest individual, the largest individual. So we say that there are n mutations between them. So how these mutations are related, or how these genotypes are related to phenotype, to the body size. So we need to make one more assumption, that phenotype is proportional to the number of mutations. The number of mutations k, it's in fact our space variable x. So we say that our phenotype is proportional to the number of mutations. In the other word, our phenotype is proportional to the space variable x. So in fact, here in this sense, now we put here our variable x is phenotype. So we have this phenotype which is here proportional to the number of mutation to the space variable x, and then we obtain this distribution already with respect to phenotype. So if we take now the body size, if we measure now the height of human individuals from the smallest to the largest, we'll obtain a distribution like that. So if you do that, then the next question is, why in this case we obtain such a distribution? Why, in other words, why there are more people with average height and less people with like small, very small, and very large? Because behind this phenotype which is here, which is there is genotype, and genotype for us is a sequence of letters. So if you take all the sequences, so there are only very few sequences here, only very few sequences here. In fact, one here, and many sequences in between. So this is what is important to understand here. Why there are many of them in between? Because if you take k mutations, the number of mutations is k, so there are many different sequences with the same number of mutations. So there are many different ways to obtain these individuals with an average height. There's only one way to obtain the smallest, only one way to obtain the largest, but many ways to obtain these intermediate waves. So this is how, well, in this interpretation, phenotype is related to genotype. Why we have such distributions for the phenotype, for example, for the human height or for all other morphological characteristics. And also what we should note here is that, and one of the interpretations also of this book, that in fact, you remember we started with a model, we tried to develop a model where phenotype is transmitted from parents to offspring, and it didn't work. So we conclude that this is not phenotype which is transmitted from parents to offspring, but this is a genotype. And phenotype is just a realization of genotype. So we started with this when we discussed this phenotype model. It was an equation like that without convection term. Equation like that, like classical reaction diffusion equation with this diffusion term, with this logistic term. This equation does not have solutions like that, but it has waves propagating this way and this way. I will also give some comments on that. Well, very shortly about mathematical proofs. Again, it's a quite sophisticated analysis behind this existence and stability results. Of course, it is. I cannot discuss it now. It would be too long. So just 2 words about that. So in fact, this is our equation in the stationary case. We consider such new variable, which is this u prime divided by u. We obtain another equation for this new variable, and then there's quite subtle analysis of behavior of solutions at this equation at infinity, and like that we can prove the existence of all these solutions. Stability of solutions is studied by quite usual, quite conventional method of lower and upper functions and comparison of solutions. So I stop on that for about the methods of proof. Another interesting question here is about normal distributions. What is also known is that if we measure, for example, human height, well, normal distribution gives a good approximation, but this approximation is not exact. In fact, it gives a good approximation here inside, but the approximation at the tails of this distribution is not already so good. The real data are larger than this normal distribution. So normal distribution underestimated. I took this comment from some internet site. So they say that normal distribution underestimates the probability of rare events. So rare events here, these are the tails, and in fact, in reality, this decay rate is not so rapid as in normal distribution. So normal distribution is here. What we obtain is here. So this is larger than the normal distribution. There are different hypotheses why real data are different from the normal distribution. And I will not discuss it now, these possible differences, but only will bring your attention that in our solution, we obtain indeed the distribution which is larger than the normal distribution. And why it is larger? Because there is this x to the power r, and r is related to the reproduction rate. So in our model, this distribution is larger than the normal distribution because of the reproduction. So this is one of possible explanations of this difference. And well, it will be, I think, probably the last, or maybe, I think the last comment, the last question I would like shortly to discuss. In fact, the comparison between these two different equations. So the equation on the left is the usual reaction diffusion equation with the logistic term, and at the right, this equation we discussed today with this additional term, which changes the behavior of solutions of this equation. So what we have here for this reaction diffusion equation, it's really very well studied during already almost 100 years, from 1930s, when the work by Kolmogorov, Petrovsky, and Piskunov appeared in 1938. And a huge amount of studies after that. What is most important here? That this equation has solutions like waves, like that, which propagate with certain speed. What are the properties of such solutions? First of all, we know that solutions like that exist, and they exist for all values of the speed greater than or equal to the minimal speed c0. And then we also know that all such positive solutions are stable. And we also know that if we take any initial condition with finite support, then the solution of the Cauchy problem will converge to the wave with the minimal speed. So, and what now happens with this equation? So in this case, we don't have waves, but we have pulses. But otherwise, there is some similarity. So here we consider in some sense as parameters the wave speed, but in this equation, our parameter is the value at the maximum. So there is a value at the maximum, I call it A0, such that positive solutions exist for all values at 0 greater than or equal to this value. if we take the value of this parameter less than the critical value, then the solutions are not positive. The alternating sign, by the way, it is exactly the same as here. Existence of waves of a variable sign for the value of C less than the C0. Then, as for the wave, all these positive solutions are stable, and also as for the waves, if the initial conditions have finite supports, then the solution converges to this, here to the minimal wave, here to the minimal pulse. So this is all about the comparison of these two equations. So yes, well, of course, there are many possible generalizations, and I think, well, this was only the first work we did. It's in fact, as I mentioned, it's our recent work, and it's in fact even the first presentation of this work in the seminar. But of course, there are many generalizations and developments, particularly for system of equations and for other models in population dynamics. I will not discuss it today. And finally, my final remark is that since we know now that we proved, we can say mathematically, that biological species exist, then I think thinking about ecology, so our important goal is to preserve this biological species, and not only in the museums as shown like that, but maybe also in nature. And on that, I thank you for your attention, and I stop my presentation. This is finished for today.
Well, thank you. Thank you very much for a very nice presentation. And we have time for questions.
Can I stop sharing screen, or we need slides for?
Yes, you can. You can stop sharing screen, of course.
Yeah. Thanks.
Okay. So questions, please. Maybe I have some.
Sorry. My question is about stability of this solution. So you have a kind of normal distribution type curve, and it is stable to small variations will disappear because of its stability.
Yes, this is right. Not only, in fact, it is stable not only with respect to small perturbations. It is stable in a stronger sense for this fast decaying solutions. For all initial conditions with finite support, as I mentioned, but not only with finite support. But for a large class of initial conditions, the solution will converge to this fast decaying solutions. If we take slow decaying solutions, like with polynomial decay, then we take initial conditions which have the same polynomial decay at infinity, but they are not necessarily close to the stationary solution. They are close to the stationary solution at infinity, but not necessarily inside. And then, so it's stability not necessarily to small perturbation, but in the sense which I described now.
I see. Thank you.
Okay, more questions, please. Maybe I will have one general wondering. You see, your equation is kind of diffusion equation, so it's kind of spreading in the unbounded volume, right? So do you have kind of estimation of influence of boundaries or limits for this?
Yes. So yes, as far as I understand your question, so well, here what I presented today, we consider these equations in the whole axis. So in this case, there's no influence of the boundary of the domain. Of course, there's as we discussed, behavior at infinity is very important in some sense and can be considered as the influence of infinity. We can say, if we consider a bounded interval instead of the whole axis, and in fact, when we, for example, in numerical simulations or in various applications, of course, we often consider a bounded domain. So the usual situation is when we consider a parabolic equation, like for example, a reaction diffusion equation with wave propagation or with solutions like a pulse. So when the solution is sufficiently far from the boundary, so the influence of the boundary can be neglected. And it is the same, more or less the same, as to consider this equation on the whole axis.
Can you make some prognosis? Oh.
Yeah, please.
Yeah, no, go ahead, please.
I just wanted to say that, of course, in some sense, we should take into account the boundary. In some cases, we can neglect the influence of the boundary, but we should, well, it should be, in each particular case, we should be more precise about that.
I see. But can you predict growth population for some special species, or maybe for human being? Because, you know, I just came back from a conference 2 days ago from Moscow State University. People said that there are estimations on 12 billion people total can live on the earth. And some people, you know them, some rectors said that not more than 8 billion people could live on the earth. So,
well, I have some comments about that. First of all, what I presented today, well, it does not give an answer to this question. Well, some models which I mentioned, some models of population dynamics which I mentioned, in particular this exponential growth or this logistic growth, I think it's the beauty of mathematical modeling. It does not give an answer on this question. It's a very simple experiment. You type wolf population on the internet, you open the Wikipedia article, and it gives you exactly this three possible answer. It can be either exponential growth or logistic growth with saturation, or, well, in some sense, pre-predator growth. It goes through the maximum and goes down. And the answer is everything can happen. So there is no answer to this question, and I think that mathematical modeling has a really very limited possibility to answer this question because all mathematical models, well, it's kind of philosophical questions. They can give a reliable answer when we model some repetitive processes. So if we have 100 experiments of world population growth, then we can model that. If we don't have such experiments, we cannot reliably predict what will happen. And the reason for that, this is more or less clear, because when we take the logistic growth with saturation, in this logistic growth, there is term 1 minus u. Well, in population dynamics, well, usually dynamics, it is usually written not 1 minus u, but they introduce carrying capacity, k. So to make it simple, carrying capacity shows available resources. How much resources are available for the population?
You mean the same k that you had as a power, u to the k?
No, not the power. Well, it's logistic term. It's u times 1 minus u. But it is usually written, well, I skip some details. U instead of 1 minus u, capital K minus u.
Okay.
Capital K is carrying capacity. Simply speaking, how much resources we have. The problem is that human population is different from animal population by the fact that we cannot estimate resources, because we all the time during the human, especially last 200 years during this technical revolution, we find new and new resources. Like you can think whatever you like, gas, oil, electricity, whatever, nuclear power. more and more resources. So we don't know how much resources we have, and this is why we cannot predict how much the population will grow.
Yeah, and also we consume more than we need.
Well, this is also a different question, but okay.
But
Thank you.
I think that resources may mean also the resources to destroy, not only to consume.
Okay. So maybe more questions. If there are more questions, please let us know. Because so many people, I cannot see all people on my screen all together. So.
But usually, if there is a hand raised, then it can.
Yes, sometimes
you can
sometimes I can see, sometimes not. I don't know why. Okay. Well, but okay. I guess we had very nice discussion.
Well, I have a small question.
Okay.
Sorry, I was late, but yes, Vitaly, hello. Could you please give some comment about multi-dimension variant of this problem? Because well, we have lots of genes, so every gene can yes.
Well, okay. The answer is very simple. I don't know. Well, in fact, well, I thought a little bit of that. I think that we can derive a model, indeed, as you say, not just with one sequence and with one set, because we consider just letters A and B, right? So one, in some sense, like one, it's not that one possible mutation, but like one-dimensional array of mutations. If we introduce other possible mutations, like for example, 3 letters or 4 letters A, B, C, right? Yeah. So then we will probably obtain a multi-dimensional problem. But first we need to derive such equations. This is not done. And then we can study such equation. I expect that we, under some assumptions, we can obtain something similar. And if we consider a similar equation, for example, in 2 space dimensions, I expect that we will have also kind of a pulse solutions like that. But this question, in fact, is completely open, and well, I can only make some hypotheses. This is not studied.
Because my question was because of a few days ago I spoke about with chemists, and they they solved one problem, and they when they realized that they have many dimensions, they very fast went to the infinity dimensional problem.
Well,
yes, and they were lucky with this. They have some results. So maybe here, transition to the infinity dimensions will give some insights.
Yeah, well, difficult to say. So let's first study one-dimensional problem, maybe then two-dimensional, and then from 2 to infinity. So
okay.
Yeah, you see, it's a very nice subject to discuss, because I mean, this kind of equation are very exciting, because first of all, we know this type of equations, this diffusion equation, heat equation. So we can suppose that we can figure how to solve them, how to handle them. But of course, your questions that you raised are much more deeper, because you have to deal with a lot of initial data. Not all data can be formalized mathematically, as I understand.
Yes, of course, but still, I would like to again, what I tried to do during my presentation, and I'd like to stress again. So there is an important difference between the usual reaction diffusion equation and this additional equation, and this equation we discussed today with this convective term which contains x. So this x is very important, because we consider an equation with an unlimited coefficient, and this change completely the properties of
I see.
this equation.
I
So
see,
this
I
is, from the mathematical point of view, this is the main point. The coefficient of the equation is not bounded.
see. Okay. Okay, thank you. So more questions, please, if any. Well, as I said, we had very nice discussion. We thank the speaker for very nice presentation. Let's thank speaker. Very nice talk.
Thank you very much.
Yes,
So,
thank you. Thank you again for the invitation, and have a good day. Bye.
You too. Thank you. Okay, bye.